And the simplest way to solve this problem, you want to do the computation over encrypted data, but it turns out to be just too much. It's gonna take, and I did some back of envelope computation. Even use most up-to-date technique, you may take, let's say, 1 billion years, or maybe 100 million years. Alternatively, you can, if you have 100 million computer, you may take 1 year in order to align one person's DNA, right? So it's not a good idea. So what are we gonna do? So we believe cloud is just given the time limit, I will quickly go through these things. And we believe cloud is special. It's designed for simple parallelizable tasks. It's extremely good at processing a large amount of data, and it works in a hybrid way. In other words, and what you're doing in the cloud is typically you have some computing resource within organization, right? And you don't want to do everything at the cloud. If the computation is highly sensitive, we just do it within your organization, and only if the things you think can be outsourced to the cloud, and you and put in the cloud, right? And also the problem is special, and the added distance we care is a small one. By taking advantage of these two facts, and then we use a special technique which calls state extension, and to solve this problem. Our idea is to break the computation into two parts. And the part which only touches just non-sensitive data, and we give it to the cloud. And the part which we will work on sensitive data, and we'll keep it within private cloud, right? And the way to break up this computation, and at high level is pretty simple. We just using this fact which calls state extend. That is, if we compute added distance. Added distance means, and you have insertion, deletion, and replacement, right? And one observation is if the distance is d, and you break the rate into those short sequence into d+1 segment, we call seed, you can get at least one exact match. So an example here is if you remove one nucleotide, and you insert one nucleotide, and you replace one, right? Then you get a new sequence. Compare with the older sequence, the added distance between these two things are 3, because you have one deletion, one insertion, and one replacement, right? But so what we can do here is we break this, a sequence into 4 segments. Each segment we call a seed, right? And remember, with added distance 3, and you break into 4 segments, 4 seeds. I can guarantee you, compare with original sequence, you can find one exact match, at least one exact match. Right. So the beautiful things here is using this approach, we can convert the original problem, which is difficult, that is secure computing added distance. We can convert this problem into a simpler one, that is an exact match. Secure exact match, which is much simpler. So what we can do here is we can have a long reference genome, right? We can break a read into small pieces into seeds, and then use it to scan the whole genome until we find a bunch of possible locations. Then at each location, we can extend it to its fullness, right? And compute added distance until we find the right position, right? So this approach called state extension. So the whole idea here is we can take advantage of feature of cloud, public cloud, which is simple, parallelizable, and can handle a large amount of data-intensive computing. And while the private cloud is, we can let public cloud to do the seeding, right? It is involves a lot of computation, but it's relatively simple. And then let private cloud to do extension, and that amount of computation, that part of computation is complicated because you have to calculate added distance. But, it involves only a small amount of data. So here's what we did, and we first, for giving each read, right? And we break it into seed. Then we encrypt the seed. Actually, we compute the key hash value, but you can treat it as encryption. We encrypt those seeds using a deterministic encryption algorithm. The whole purpose is with the same piece of data, if we encrypt it twice, the ciphertext, the encrypted text will be identical, right? And then for the reference genome, also according to the length of seed, and we extract those short small sequence, encrypt them, right? Then send it to public cloud. Then we let the public cloud to do those exact match, to find out the possible location of, those short DNA sequence, and using those exact match. Then after exact match is done, it will send the result back to the private cloud. Then in the private cloud, you know, just what we're going to do is, and we go to those locations, extend it to full length, and you know, just and find out the right location. That is the location, the read and its counterpart on the reference genome looks very similar. They are within a small added distance. So that's the idea. That's the high-level idea. You know, just and we do the further work. You know, just we study how to make these things efficient, and we did a study. We did a security analysis and make sure this is secure. You know, just and intuitively at the private cloud, and you can see nothing but encrypt the data, right? Just encrypt the seed and encrypt reference sequence. But you know, just and there could still be some thread, just like you know, just and we call frequency analysis, because you know, just and the different seed will be different, and encrypted sequence will be matched and with different time, right? You know, just and maybe using this frequency analysis, this frequency information, which is a piece of side channel information, attack can figure out something, right? But in our research, we showed, you know, just because of unique structure of human genome, attack cannot get anything, you know, just by looking at the frequency alone. So we analyze, we implement, we build these things, and over Hadoop, right? And we evaluate our stuff on the, you know, just on future grade, right? You know, just you guys know future grade, right? It's a big cloud test bed across the country, supported by NSF, and we have a bunch of machines at University of Chicago as a public cloud, and we have a single machine at IU as, you know, just private cloud. And we did a security analysis and working on the real human DNA data, right? You know, just and the result here a little bit opposite. Actually, we do the whole genome analysis and trying to map 10 million human microbiome data onto the whole genome. And the result is, you know, just we can successfully outsource, you know, just over 96% of computation to the public cloud. You know, just and in a privacy preserving manner.